Okay. Hi, everybody. Hey, it's Bridgette Lyn Dolgoff, and today we're doing Think Collaborative, and we're collabing, and today is going to be the second conversation on numbers. So, hey, Ryan, since you sent the video, also, for those of us that don't know about the video, there will be a link for Ryan's video that he sent in and that I uploaded because he wasn't sure he was going to be able to make this collab and he wanted to participate, but it turns out that he can. So bonus with the video. Okay, so you want to talk to us about the video? And I just want to say, Ryan, when I was looking at the board and trying to figure out what you were doing with all the numbers, I kind of had to let my mind go. And then it sort of came to me. You can tell me if I'm right or wrong because I'm a math tard. That you were configuring the values of, the different, A, D, and so forth, and then using the matrix, which is really cool. But it also kind of, once I kind of let go of it, it kind of reminded me of Sigil magic type stuff, where you configure the language that you want to use for your Sigil, and then you have to get it all written out, and then you kind of have to design it and put it together, and then you come up with your Sigil. So,
well, in that sense, kind of any avenue of learning is sort of sigil magic, because we have to, whatever problem we're approaching, we have to figure out how we're going to frame it. We have to, come up with some kind of sensible language or schema for framing the problem, and then we have to, I don't know, introduce something, invent a white knight that's going to solve our problem for us, right? In this case, it was just fleshing out, okay, I'm looking at this sequence in twos, in just pairs of consecutive terms. And that gives me this linear system that I can just apply iteratively. But the magic of that was that it's an invertible linear operator, and I can actually get it to have simultaneous eigenvalues, an entire basis, so an entire coordinate system for the plane, consisting of vectors whose direction doesn't change under this operation. Well, the second eigenvector direction did change because it was flopping. It had a negative. It's flopping back and forth. But it's contracting each time. And then the other direction was expanding each time. And I'm just trying to show you guys that in the limit, the only part that matters is the component that's getting stretched and stretched and stretched. So anyway, that was a follow-up to what I was talking about last time in terms of that. And I realized as I was talking that it just wasn't going to be a very good explanation unless I had the ability to write something down and kind of capture it a little bit mathematically, actually. And that's a consistent problem in speaking math. You can't really speak math only. You really actually have to jot some things down at certain points.
So Ryan, can you explain to folks what eigenvalues and eigenvectors actually are?
So so an eigenvalue and an eigenvector are going to be paired. In this case, it was a particularly nice case because I have a two-dimensional system and I have two distinct eigenvalues. And so what that means is under some coordinate system, there are going to be, our coordinates are going to be special in the sense that our we want to arrange our coordinate axes to coincide with our eigenvectors, because the direction, the one-dimensional subspace determined by this vector, is going to be invariant under the linear transform. So, like in the case of that one phi direction, that was the main thing we were interested in that example. That line, that one-dimensional subspace, is getting stretched out in both directions by a factor of phi every time we apply the operator. But the line itself is remaining invariant. Same thing with the complementary line. That line, well, it's going to get reflected across the origin every time that we apply the operator, but it's actually remaining an invariant subspace. It's just flipping and contracting every time. And so by expressing our coordinates in terms of these special directions where the linear operator basically just acts like a scalar, we can simplify the problem down. So diagonalizing matrices is really just a computational technique that we use to simplify matrix algebra.
Okay, so I kind of have a question, right? Because, you know, I don't really understand any of it, but I thought it was really interesting, right? And I really love that you used a board, you right? And you kept, you know, reconfiguring everything, you know, so you could scale it down right into your mathematical equation. So can you take anything and create a coordinate for it?
Well, so there are some operators that wouldn't lend themselves to this as easily. And I did sweep a lot of that kind of stuff under the rug. Basically, I was assuming a fair degree of proficiency with linear algebra coming into that, because, well, at a certain point, you just can't backtrace and explain the roots of every single thing you're doing. But yeah, there are linear operators that don't decompose exactly the same way. So what I said I was using was the spectral theorem. I'm actually using a much lower tech version of the spectral theorem to say that I can actually break the plane down into two orthogonal eigenvector directions. The one thing that makes it easy, and in this particular example, it was easy because we had two distinct eigenvectors, and the eigenspace for each, eigenvalues, and the eigenspace for each, which is just the span of that, you know, eigenvector, was one-dimensional. So there's kind of nothing too bad that can happen in a case like that, because if you think about it, okay, one direction is getting expanded by a factor of phi every time. Another direction is getting multiplied by a factor of minus phi inverse. Now, if you had some linear combination of those two things, if they weren't completely orthogonal, completely independent, then well, it becomes obvious that you're actually changing the direction of that vector, because you can't scale one component by one scale and scale another component by something completely different and stay in the same one-dimensional subspace.
Okay, so I have another kind of a question. So you use the word operator, but so when you're operating, like in mathematics, like what you're doing is that you're kind of also kind of like the creator too, right?
Well, in mathematics, you're always the creator, because you can make up anything. We just call it a definition. You know, you just
Oh, there
you
it
want to
is.
construct, you just define it to be so,
There it
and
is.
out what the consequences are.
There it is. You can create anything. So even in mathematics, you can create anything. No.
Well, it's true. And mathematics is something that we can completely make up. We cook it up in our minds, and then we just insist that it be logically consistent with itself. And that's where it all comes from. You can make up any silly definition you want. It may not turn out to be something useful to study, but you can certainly make it up.
So by making up a definition, do you mean describing something in a mathematical equation?
Well, so a definition is usually just a definition, doesn't even involve an equation. So, I mean, I can define some new term, or I can define, like I did, just define a linear operator to be applied recursively.
Okay, so we're picking on you because, Lenny and I, well, I'm probably more retarded than Lenny, when it comes to numbers and math, because I have like this weird stuff with numbers. Like some of them get along, some of them just don't get along. I prefer not to deal with the ones that are complicated and start fights with other numbers, so I have kind of some psychological issues.
You're a synesthete.
I'm a what?
You're a synesthete.
What's that mean?
Yeah. So, some people see music, some people, like the human calculator, they call it. This guy, he's a British dude. He's, I think he's got Asperger's or something. But he feels numbers, and like he has like these strong, I guess, emotion type attachments to numbers, but he uses it in a way to where he can do calculations as fast as a calculator, literally.
Okay, well, I'm not that good because I can't get over the hurdle of some of the personalities of some of the numbers. So, okay, another kind of interesting word that you use in math is when you're doing stuff is decompose. So what does that mean exactly? So you're just breaking it down until you can create an equation with it or a form?
Well, so there's a couple ways I can decompose. It mainly comes down to choosing a coordinate system for the plane in the case of, because everything I did was only two-dimensional. So a coordinate system itself is a way of decomposing the plane, because you have to pick a direction and you have to pick a orthogonal direction to that, some perpendicular, assuming that you want rectangular coordinates, you pick them to be perpendicular to one another. But so how you choose your coordinate system has everything to do with how you express the points in the plane. And it also has everything to do with the form that your linear operator is going to take as a matrix. It can look simple or it can look complicated. And that's why I wanted to change the way I was expressing points in the plane by changing my coordinate system in such a way that it simplified the operator I was trying to apply, or the expression of it, right? Because then I got a diagonal matrix, and if I want to take the nth power of that diagonal matrix, I just put the n on top of both of the eigenvalues.
So your coordinates are the things that you pick. Like in the algebra setting, you had, three, things that you were kind of breaking down to. So you had the matrix. Would that be considered a coordinate? Like what exactly is the coordinate?
The coordinates are just your x and y.
Okay. All
So
right.
when I'm talking about like starting at a coordinate position of 0, 1, right? Well, that's just saying that I'm starting with the 0th entry of this sequence being 0, the first entry being 1. But that's just a vector in the plane. That's a point. Now, if I expressed it in other coordinates, it would look different. It would have a different coordinate expression. It wouldn't be just 0, 1. So basically what I had in that final picture where I have the coordinate plane and then I have a couple of green lines is I have like a rotated coordinate system. Well, that's the new coordinate system that I transformed to in order to solve the problem, are the green lines. And so you can think about that. If you take any two-dimensional space, you just draw a vertical line and a horizontal line to depict your Cartesian coordinates. Then you can just tilt your head slightly and you get a completely different idea of what that coordinate system is. Any different rotation of that coordinate system will give you good coordinates for the plane, but they don't always align with what you expect them to be. In this case, we're aligning them with something particular to the linear operator that we're iterating.
Okay, so you say you only took the equation, to a 2D level, right?
Yeah, I was only interested in using two variables, or I mean two indices of the sequence, because what I was getting at is actually the ratio of consecutive terms. And so all I need are I need a reference point with two consecutive terms of the sequence, and then I can consider where they're going in the plane, because the slope of that line, that first eigenvector direction, is what determines the fact, because after iterating this operator a sufficient number of times, the dots of the sequence are approaching this line tighter and tighter, then we can say that, well, the ratio of consecutive terms is approaching whatever the slope of this line is, which happened to exactly be phi.
Okay, so tell me what phi is.
Well, phi is the golden ratio, and I wrote it up there.
Okay.
It's that 1 plus √5 all over 2 number.
Mm-hmm.
But it is this naturally occurring, and there are different ways of getting at what phi is, but that's particularly the way that connects with the Fibonacci sequence that I know the best.
I'm just putting you on, you're our numbers expert today, so I'm putting you underneath. So that way I could...
Talking about that, I was really trying to clean up what I had talked about last time.
Yeah, well, it was just, it kind of actually, for me, opened up a whole other kind of reality because, number one, well, we talked about earlier in this conversation is that, math is a way of explaining something, but it's also made up, right? It's a made up explanation. So that's good to know. But the other thing too, I was kind of...
Same as any language. I mean, English is made. All of it is made up. We just have to have the same understandings of what the terms actually mean in order to communicate meaningfully, right?
Right. Well, and that's why I don't really know a whole lot about numbers or the definitions, and so that's kind of why I'm asking you about like the certain words, and I'm kind of grasping a whole kind of like new idea about math, as a language, to communicate. So the other thing that I was kind of blown away by your video was that you could take the matrix and turn it into, right? So here's the matrix, and then now I've got a little equation for the matrix.
Well, matrix are just part of linear algebra, and it's one of the tools that's used in linear algebra in order to get things going. A matrix is just another form of transformation. But I did notice that there's a lot of terms and numbers in mathematics that don't apply to numbers, but just apply to mathematics. And sometimes when Ryan's talking about the mathematics, he slips into mathematics jargon, which doesn't quite make sense to a lot of people. Like when he was talking about scalars and scalars versus vectors. That's a basic math concept, but I'm not sure how many people out there really know the difference between a scalar and a vector.
Well, and one thing that's okay, so as scalar, I was referring to the actual eigenvalues, because along these particular directions, the linear operator acts as a scalar, which means that it acts as multiplication by a number, and that's what I mean. So when I'm saying that, okay, that first eigendirection gets scaled by its eigenvalue, which is phi, I literally mean that we're just multiplying everything by this factor. And because it's bigger than 1, it's causing that entire one-dimensional subspace to expand. What's interesting, though, so we think of, a scalar as just some number from your underlying field that you can multiply anything by, whether it's a vector or a matrix or whatever.
But, is it a dimensionless number?
Yeah, well, we kind of think of scalars as being zero-dimensional, yeah. Because when we're dealing with vector spaces in particular, the scalar is a homothety. It applies to everything equally. It doesn't single out a let me back off of that and explain. Linear operators are matrices. Now, actually, so when I talk about a linear operator, it's just an abstract thing until I put coordinates on it, and then it becomes a matrix. In finite dimensions, it becomes what we call a matrix. Because once we have a coordinate system, then we can just put coordinates in and capture exactly what this linear operator is doing in the form of a matrix. But what these things are, these linear operators or matrices, are kind of like higher dimensional numbers. So when they act on a vector, say, they don't just scale it up or scale it down. They may scale this direction by some amount and then invert this other direction and do something else in a different way. So they're a lot like numbers. They're a lot like scalars, but they respect different directions. They have, different transformative effects on different subspaces of your vector space. And using that fact is the reason that we even bother with finding eigenvectors at all.
Okay, so I have to kind of, because I'm a filterer. We all are filterers of information, and we have to filter that information, in a way that, I can glean it and collect it and harvest it and put it into something, right? So there's just a couple things that kind of blew me away listening to Lenny and you. One was, subspace to expand. And then the other thing too is like, I know that you're using the word matrix in a, mathematical way, not really like, in a quantum, I guess, kind of way, like the movie The Matrix, even though there's probably similarities, that are, like in the background. So
well, that's absolutely referring to a matrix, like,
yeah.
In the mathematical sense, some giant array within the computer simulation system that behaves like a matrix, because matrices are used in computer programming all the time.
So, I mean, okay, but so matrix, transformational, and then, so in math, matrix is used, I'm just going to throw this out there. You guys can tell me what you think about it, because I'm kind of like, my head just kind of broke open, and I'm kind of expanding here in my own reality. So matrix transformational, so could the matrix in math also be a transformer? And then, think about that, because we use transformers to change the electrical current, from one house to another, right? In different forms of electrical energy. Transformers could be, shaman people who transform, reality. Transformers could come in mechanical, all different kinds of stuff. So could the matrix mathematically as a transformational dealy Bobby, could it also be considered a transformer, like at the very core?
Yeah, well, we call them linear transforms. Sorry, there are different terms. Operator, I get used to using the word operator because at a certain level you study them at a higher level as operator algebras. But what what a matrix essentially is capturing a linear transform. So it has to be linear, but it is this one type of just a way of transforming space. And everything that we talked about was finite dimensional. It doesn't have to be. There are bounded operators over any kind of, any ordinal you want. You can construct a vector space with an ordered basis that counts up to that ordinal, and you can talk about bounded operator. I mean, topology in the situation, but you can talk about transformations of infinite dimensional spaces, in other words, and they can achieve all sorts of different things. In fact, sometimes we do use, something, you're talking about an electrical transformer, and I'm not, what the physical component is doing is one thing, but one thing that we use, because we have this 60 hertz frequency, we have alternating current, and so there are waves. There are basically sine waves involved in everything electrical. One thing that we have to use is a Fourier transform, which is a linear transform between function spaces. So vectors don't have to be what you think of, just like these geometric. Sometimes they're functions. You take the space of continuous functions over some topological space, and that becomes its own infinite dimensional vector space, and you can apply, say, a Fourier transform into the function space over the dual. It becomes complicated, but
so I just have to say, I kind of had this kind of moment here where, I'm always looking for the imprints of, I don't know, I'm going to use terms of the hologram, the holograph, that we live in a computer, mathematical, now I'm like, okay, so math is at the heart of it, right? So because people can like dream up, these math equations, which can become codes that can be, applied into like the Matrix movie, a computer system, right? And the code could even be you as a biological unit. Or, whatever that code's going to be. So basically, when I'm going out on a limb here, math and people that are doing math may be ultimately creating our reality by transforming as an operator to the system and creating, subspace, and all these other kinds of definitions that we kind of have been talking about with math. But ultimately, they could create their reality in multiple types of levels depending on where they're at. Like you were saying, one-dimensional, here's the one-dimensional equation, here's the two-dimensional equation, here's the, eighth dimensional equation. And so that's, at the base of it, some of that stuff is being, coded and put into systems, maybe even just by thinking it.
I find it interesting that a lot of the terminology used in mathematics falls out into other areas, and the same terms are used in different ways. And it makes it really difficult to understand what mathematicians are saying because they're using words like derivatives and integrals that if you follow the financial news, a derivative is something completely different than what mathematicians are talking about when they speak of derivatives. But in a way, it's really not, because a derivative in economic terms is something that comes from another line of thinking. And so I find it interesting to talk with Ryan here and have him use a lot of terminology that is very, very specific to mathematics, and that you don't recognize that as a math term. You recognize like matrix as a universal term, and trying to fit the concept of the Matrix movie into the mathematics of matrix algebra just to me seems a little awkward.
Yeah, well, that's the thing, right? So you've got all this languaging, and then how does it like apply? But, like for me, I look at the Matrix movie, and there's two parts of the Matrix movie. Don't you in algebra you just have to have two things, right? Like, so, like, I'm not an algebra expert, but I know that, say, for example, if you want to have, X, X might be, 5 apples, but the apples are not all the same shape, so that you have to derive like, a common thing to take in the 5 parts in its totality. So, that's kind of like the way that I remember it, I think, in high school, kind of, because I asked, a lot of questions. But, like in the movie The Matrix, you have 2 components of the matrix, right? Which could be an algebra equation, and then equal is, where it's going to head. So you've got like the mainstream system that's happening that could be identified by part of the algebra linear equation. Then you've got the second part of it, which is like you've woke up and you're out of the system, but you're still operating in that system. And then you have equals, the outcome, or, the finished product of the equation. I have to think about things in ways that I can think about them, because I can't, math is just something I can't grasp. And if I try to look at numbers to grasp stuff, then I don't want to deal with it at all, because the numbers they don't get along. I can't even talk to them. I can't even say, hey, number 3, will you go over there and times 2? and 3's like, no, I will not, kind of a thing. So for me, it's like I have to try to figure out what this looks like, you know, in other spaces and places and form, I guess, you know. But it is complicated because, like you were saying, Lenny, derivatives are in the economic and banking markets, right? The matrix is the, you know, maybe we could call it the system that's happening all around us, the hologram, right? The holographic system. Then you have like an operator. What would an operator do? Well, they could be operating heavy equipment. They could be a telephone operator. They could be a government operator, you know, dealing with control of information, which is language and numbers. They're just the words that are used in math, which kind of start to make me feel like that math may be at the core of a lot of things, because a lot of different arenas and avenues use their words similarly, you know? Anyway, that's just kind of my crazy thoughts.
Yeah, I find the application of numbers in a quantitative sense, where you're counting and adding numbers or multiplying them, makes sense in a certain way. The measurement of numbers in a qualitative sense, like you're talking about how the numbers don't agree with you or don't listen to each other, each number has its own qualities that come about to be part of that number. And it sometimes gets me to thinking that maybe numbers at the very base of the number system, 1, 2, 3, are different than numbers that are greater, that measure the quantities, that the concept of 1 is a difficult concept to grasp. And in the Fibonacci sequence, where there's two different ones, coming up with a qualitative understanding of the difference between those two ones is not a mathematical function at all. It's one of those things where when you're applying 1 to something, you look at it as an individual, but like your apples, each of the apples are apples, so you have a group of 1 that contains all apples in addition to each of the apples being its own 1. And so there's a lot that we learn in school about mathematics that guides our thinking, but then leaves us off at the level of mathematics that we achieved during our working time in the school or in the work. And so I think that a lot of different people see math as a challenge rather than as a means of describing reality.
I'm operating subspace right now. Ryan, are you there? Did you leave? Did we lose you? Ryan, hello?
What is going on here?
Okay. Now we can hear you.
Now you can hear me? I don't know. I've been talking this whole time. I kept wondering why I was getting interrupted.
We weren't hearing anything.
You guys shut up. I'm trying to talk and we can't even hear you.
Okay, so, all right, I'm just going to jump back in the last point I was trying to make because, yeah, I was asking you guys if you could hear me because I'm starting to get weirded out by the whole thing. Anyway, yeah, the 5 apples doesn't make sense until you can actually identify different things as being the same, right? Because they are not the same thing at all. But you have to identify them as being different examples of the one form, right? If you want to get all Platonic about it, but you have to have this identification of disparate things in order for numbers to start to make sense at all, right? From an intuitive standpoint. And I mean, in that sense, I mean, numbers exist only in our heads, and their entire basis is a lie when it comes to physical reality, because we're identifying things that are not the same.
Well, isn't that how we get into group theory and create groups? Is that we identify things by grouping them into the same group or into different groups?
Well, right. And as soon as you start grouping, then you've gotten into addition. Because they're the same thing. The addition operation and grouping. And I was talking about this last time, and it plays right into something you were just saying, Lenny, is right. The most real numbers, I should say, like I just said, they don't make sense at all until you tell yourself a lie. But the most real numbers for us as human beings are just 1 through 7. Everything above 7 gets kind of abstract because we can only get there through grouping. And we have to have this innate sense of addition in order to even make sense out of the higher numbers. And I mean, this counting operation that we do as children to even get up to higher numbers is what? It's just an iterative addition by 1, but it's all addition. And when we understand, I mean, so we have these certain operations that have somehow come about as being intuitive to us in our minds and the way that we process things. Right? A number system and, you know, a few binary operations. And we just kind of study the logic of that and some of the applications.
Oh, you just got cut off again at some of the applications, Ryan. I can't hear you. Hello, Ryan.
Back?
Oh, there you are.
Yeah, every time my phone sleeps, it's doing this. I don't know why. It just decides different ways to screw with me. So
That's
anyway,
part of the matrix.
yeah. I'll let you run with it, Lenny or Bridgette. Somebody.
Well, I was thinking about so early on when I had met Ryan, we had this kind of he kind of more of a shamanism type, you know, geometry and numbers and kind of a conversation. And one of the things that I really gained from that conversation was that looking at numbers, even, you know, as a number, right? So even the number 1, even if it's just one dimensional, if it's 2-dimensional, it's 3-dimensional, you know, it has sides. 1-dimensionally, it just has one side, maybe a little, you know, doodad, doohickey up the top and a doohickey down across the bottom, or it can be singular. And then, you know, the geometry of what that would look like, you know, you can go into like the hexagons and the octagons and all of that, and then you can go into more refined geometrical patterns, and then you could also go into like Emoto and then the patterns that he discovered from language and sounds, which sounds could be numbers as well, on water, right, that he imprinted onto them. And so one of the things I learned early on was that to look at the surface, you know, like the surface volume, and to see, you know, how much surface space that it has, because the more surface space that it has, for example, to, you know, could be the same as 1 as far as surface space. But you get into things like 3 or 4, and then you start to see that there's a lot more surface space, just even on the actual number, even if you just look at it in a one-dimensional way. And this, I kind of translated into plant and earth medicine work that I do, because I started to realize, like, say, for example, a leaf on a tree, like you may have a huge leaf, right? And if you look at it in like a one-dimensional, way, it has a certain amount of surface space. But then you could see another leaf that's like half its size, that has all these other cuts in it and has all these different other grooves in it, because it's more specific to desert and windy areas. So the trees learned how to, create leaves that do better in the wind, more aerodynamic, and also, they may be more drought resistant leaves, so they might have, more areas. And so I started to realize, like, that, just because of size does not indicate, like surface space. So even for me, like just taking that whole thing with numbers and the surface space, kind of more in a shamanistic type way, helped me to actually look at things, in the environment to, discover, how much surface space they have. And size does not always, of the thing, does not always indicate that it has a lot of information or data or surface space. Do you remember that conversation we had, Ryan? Oh, I can't hear you, Ryan. Tap on.
Here I am again. All right. Well, I do remember. I don't remember the surface space being such a big part of it, but
well, because we're talking about beings and different beings that live within those, on kind of a shamanism, right?
I remember I had this dream where this inorganic being, highly irritating inorganic being, informed me repeatedly that my number was 9, and I had to have a talk with you about it because I didn't know what the hell that meant. But yeah.
So yeah, so I mean, math.
I'm having trouble hearing Ryan.
Can you hear me now? Lenny?
I think Lenny's.
Yes?
Oh, there he goes.
Okay. You can hear me then?
I can hear you now. I was having difficulties, though, with your last couple moments of conversation.
Oh, sorry about that. I'll try to keep the phone closer.
Okay, so this is what I was going to think about doing. Because there's only a few of us, and you're the expert, is maybe closing the Think Collab early. But what I was going to do is I was going to screen share your video so that it's actually on at the end, so that and then you guys could hang up when you wanted to, and I would just screen share it to the end, so that way your math video would be a part of the actual talk. So that's kind of like where I think I'm going to head with this. So is there anything anything in particular, like, that anybody wants to add? And including, like, where do we go? Like, we're starting to learn this stuff. You were talking about how math is just created in somebody's head, and how we're creating this reality. Like, what should we think about in order, like, from a math person's perspective, like yourself, Ryan? Like, how should we think about things, like, in a way mathematically, or that we can actually change things and actually move forward for, like, the good or the betterment? It's kind of a tough question, but I can't hear you. Oh, there you go.
Yeah, you can hear me, right? Yeah?
Yep, good. All good.
So well, okay, there are a couple. So I'll get back to that. I was trying to say this earlier. Maybe you weren't hearing me, but I think what you were talking about with the numbers creating reality, or mathematical concepts basically creating reality. I think we're seeing that creating strata of reality. In fact, I think we're seeing all of this from the tech industry and from the different social media and different platforms that people have really taken as life surrogates, right? And I mean, that is their reality. That's their strata now, is fucking Facebook, right? And so what we can do is get out of that kind of a mentality and start critically examining the data that we are feeding Google's AI and different people's AI, right? Well, they've got these machine learning algorithms, and they're training and training and training to hack your brain, basically, to get inside your skull and anticipate your needs before you have them. So the advertiser is right there on the spot, right? And we already know what they're doing. We already can see the different layers of security and surveillance that are being built up around us digitally. I mean, I think the sinister aspect of how it's being used to shape the world is pretty clear. And I don't want to tell people what to think about. Like, in terms of mathematics, I think about what interests me. But I don't know. I don't have like my own special application to ward off the digital dystopian threat. But I do keep my awareness about me, and I think that's what we need to do is to not shrug math off, and certainly not shrug logic off, which is the whole structure of mathematics. We need to commit to reason, and we need to keep our awareness about us in terms of these different things that are being done. Hello, am I still here?
I heard that. It's one of those things where applying reason to life right now seems a little bit complex, but there's also the whole area of sacred geometry. And that is, I don't know if it's accepted by mathematics or not, but it seems as though there's a whole nother world of mathematics and sacred geometry that's different from analytical geometry or the geometry we learn in school. But yet it very much applies to nature and natural surroundings. So maybe in a future collab, we want to go down that pathway and talk a bit about sacred geometry.
That's really what I wanted to hit up, Lenny, was my new thing that I wanted to trot out for this conversation, which maybe we'll just put it till next time. But I like to talk about the Platonic solids and some of their symmetry groups, because these things are particularly beautiful, and they do cross that bridge of being legitimate mathematics and also have a long history of sacred tradition.
Yes, I think the Platonic solids are extremely useful in my area of chemistry when we start using group theory to define the shapes of molecules and atoms, the atoms coming together to put the molecules in a form where physical transformation can be realized. But that, I think, is a conversation for another time.
And it's one that I totally want to hear about. And hopefully, it's kind of interesting because, having this conversation called numbers, and is really morphing into something pretty grand, actually. You know, all these different components and these conversations of it. And I'm learning a lot, so I really appreciate it immensely. But yeah, let's talk about those other wonderful things that you guys just brought up. And that way, Lenny also can get into the conversation. And then I think Learn Share, sorry, he keeps wanting to, I think, you know, talk more about his music and the numbers that he's creating in his music too. So we still have a lot of, you know, good conversations down the road. So we'll keep it going. Is there anything anybody actually wants to add? And then I'm going to put the video on so that I can actually record it on this conversation, the one that Ryan did.
I'm good for now. Thank you for having me again.
Well, thank you, Lenny, for coming. All right, Ryan, any last words?
No, same here. I'm good. Thank you, guys.
Okay. And if you guys want to hang up, that's okay. And then I'm just going to finish the record, and I'm going to start it in like 2 minutes. And then, so that's the end. So thanks, guys, for coming on and having a conversation. We're going to have, talk about these solids in the future, and also what Learn Share wants to do. And you know why I keep calling him Lean Share is because that's what his Skype name is. So I'm sorry, Learn Share, but I keep calling you the wrong name. Okay, everybody, thanks for listening. And I'm going to screen share. And I have to figure where that's at. Oh, here we go. Let me go to the different screen. Here we go. There's Ryan. You get to see what he looks like. Okay. All right. Oops. Let me go in here. Okay, let's see. Oh, maybe it's not going to let me. Okay, hold on 1 second. Let me see. Let me go in here. I want to go to switch to screen window. I'm going to do that one. And then we're going to go ahead and hold on 1 second, hopefully. Okay.
Hey, just making a supplemental video for the Think Collab. We're in the middle of talking about numbers. I guess we're going to meet again on Friday. And this is a clarification bit about something I was saying last time. So let's remember the Fibonacci sequence. I'm going to go ahead and index this Fn. F naught we take by convention to be 0. F1 is 1. And so on. We have this relation. We have a recursion that determines the sequence, right? We say that, well, if you take the nth term and you add to the...
Hey, guys, sorry. Unfortunately, I am not doing a very good job with the screen share. I don't know if it's screen sharing. I think it's not because other people left the group, which is fine. But anyway, that link with Ryan's class will be on the call, on the video that'll be on Think Collaborative. So yeah, thanks so much, everybody. Have a great day. Bye-bye.